some force is being applied on some object, it's the property of the object and duty of the object to oppose the deformation due to the force. And in case it gets deformed, it's job of the object to get reformed, means get into its original configuration after removal of the force. This is called elasticity, right? And just like elasticity, it is your duty to always remain determined towards your goal, and in case some situation, some forces, some stress, some pressure tries to deform you, it is your duty to just oppose this deformation. And in case you just get demotivated or something like that, then it's your duty to just get motivated, get reformed. So today we are going to talk about elasticity, and today's topic is relationship between elastic constants. So you know about elastic constants: gamma the Young's modulus, K the Bulk's modulus, and eta the shear modulus. And we know about Poisson's ratio. What is Poisson's ratio? Poisson's ratio is lateral strain by linear strain. What are the lateral strain and linear strain? You know about when we stretch a wire, the length of the wire increases but diameter of the wire gets decreases because volume will remain constant, and if its length is increasing, the surface area should decrease. And when we apply force along the length, the increase is the strain is alpha, but the means the increase in length by the original length is alpha, but the decrease in diameter means the decrease in diameter by original diameter is called the lateral strain. And sigma, the Poisson's ratio, is lateral strain by linear strain. So we are going to find a relationship between these four constants. So for this we are going to take a cube having unit surface area. If it is having unit surface area, means its length will also be a unity. Means let us suppose the unit to be in centimeter, then its length and breadth will be 1 centimeter, and therefore the surface will be unit, means 1 centimeter square. So now we can say that a force Tx being applied on this direction and another being on the opposite face of this, and let's first name it A, B, C, D, E, F, G, H. I am applying the same amount of force on both of its faces in opposite direction. So here Ty and Tz outwards, and another one inwards. I hope you are able to understand how the forces are being applied. So now I am going to calculate the increase in volume. Here you can say that force is Tx and the surface area is unity. So stress is force by the surface area, and here Tx by 1 will be the stress, means stress will be equal to Tx, and along this y direction it will be Ty, and along z direction it will be Tz. So now we are going to calculate the volume. For that we have to know about sigma. Sigma is beta by alpha, right, where alpha is the linear strain and beta is the lateral strain per unit stress. So beta is lateral strain per unit stress, means if I am stretching this cube along x direction, this force will decrease the length along y and z direction, and means for tx, the increase in length due to tx will be multiplied with alpha. Alpha is linear strain per unit stress. So total linear strain will be alpha into stress. Here stress is tx into alpha. Linear strain means the increase in length is tx into alpha, but due to ty and tz it will have a lateral strain, means it's recall the case of that of wire. We were stretching the wire along length and it was contracting along its diameter. Similarly, for y, the stress along y direction, I am stretching along y direction and it will contract along x and z direction. So for y stress, I will do ty into beta, lateral strain into stress along y axis, and due to this ty, the length along x axis will decrease with this amount, and similarly due to stress along z axis, the length along y and x will decrease with the amount tz into beta. I hope you are clear. Let me draw something so that thing will look more better. This is x, y, z. So along x, the tx is being applied, along y, ty, and along z, tz. So now the force being applied along x axis will obviously increase the length along x axis, but that due to y will increase along y but decrease the length along z and x, because it is perpendicular to x and z. And the force along z axis will increase the length along z axis but decrease that along y and x. I hope this thing has made this thing clear. And here alpha is linear, beta is lateral, therefore the decrease is the stress is multiplied with beta to show the decrease in length. So now what will be the length AC? The length along the x direction, it will be 1 plus Tx alpha minus Ty beta minus Tz beta. Why I have put it here 1? Because the initial length is 1 unity, plus the increase minus the decrease, increment due to the tensile stress means the stress along x axis, and decrease due to the perpendicular stress. Basically Poisson's ratio, from Poisson's ratio it is clear that the stress perpendicular to the means the length along the direction of the stress increases, but the length perpendicular to the stress decreases. So this thing is used here. Now here I have found AC. What will be CD? CD will be equals to 1 plus, here the increase is due to Ty stress, means Ty alpha, and decrease due to Tz beta minus Tx beta, and for Cg it will be equal to 1 into Tg alpha, because increase due to stress along z axis and decrease due to tx beta and ty beta. So now I have three sides of the cube. So to calculate volume I have to multiply these three, and now I know the initial volume because all the sides are unity. So total volume will be also a unit volume, means 1 meter cube or centimeter cube as per your meter. So now I am going to multiply AC with CD with CG. So let me erase this part. So this will be 1 plus Tx alpha minus Ty beta minus Tz beta into 1 plus Ty alpha minus Tz beta minus Tx beta 1 plus Tz alpha minus Ty beta minus Tz beta Tx Ty Tz. Yes. So now you can multiply the whole thing and neglect multiplication of alpha beta and high power of alpha beta, there something like alpha square and beta square, but I can make this calculation easy. You can do this and things will look real very clumsy, but you can do it directly because first I am going to multiply this thing with this thing. So 1 into this thing will obviously be this thing, 1 into Ty minus Tz beta minus Tx beta, right? Now multiplying this term with 1, because multiplying this with other term will give us some multiplication like beta square, alpha square, or alpha into beta. So I will multiply these three terms with only 1. So I will get plus Tx alpha minus Ty beta minus Tz beta. I have not multiplied these three terms with other terms because multiplying this with these three terms will give alpha into beta or alpha square or beta square, which will be negligible because alpha beta is already a small quantity, and multiplying with another small quantity or taking a square of it will give us a very small quantity, and multiplying this trace with a very small quantity will give another very small quantity, which can be neglected with respect to these terms. So this thing multiplied with 1 plus Tz alpha minus Ty beta minus Tz beta. So once again I will multiply yes, I will multiply 1 with everything and will get 1 plus Tz alpha minus Ty beta minus Tz beta, and multiply these things only with 1 because obviously there is an Ty alpha minus Tz beta minus Tx beta plus Tx alpha minus Ty beta minus Tz beta. So this is the result, 1 plus Tz alpha, Ty alpha, Tx alpha. I can take alpha common and write Tx plus Ty plus Tz, and here minus Ty beta, minus Ty beta 2 times minus Ty beta, minus Tz beta minus Tz beta 2 times minus Tz beta, and similarly 2 times minus Tx beta. So I can take minus 2 beta common and write Tx plus Ty plus Tz. So from this I can take Tx, Ty, Tz common and we will get Tx, Ty 1 plus Tx, Ty, Tz whole into alpha minus beta. So now this is the final volume after application of this Tx, Ty, Tz force or stress you can say. So the increase will be 1 minus this thing because initially the volume was 1. So the increase is minus 2 beta. Tx plus Ty plus Tz alpha minus 2 beta is the increase. Now if we have applied these means if the Tx, Ty, Tz forces are equal, let us suppose Tx equals to Ty equals to Tz equals to T, then we can say that this thing is equal to 3T into alpha minus 2 beta, right? And what is the formula of modulus of rigidity for increase in volume? Means what is the formula of bulk modulus? That is stress by strain, means T by the change 3T alpha minus 2 beta change by the original volume, that is 1. So this will be equals to 1 minus 3 alpha minus 2 beta. This is equals to bulk modulus. Bulk modulus means increase in the means the modulus of rigidity related to this modulus of rigidity related to what? Related to increase in volume. And here we have the stress as T, the increase as 3T alpha minus beta and original volume as 1. So we are getting bulk modulus as 1 by 3 into alpha minus 2 beta. So K equals to 1 minus 3 into alpha minus 2 beta, and now I can write, I can take alpha common, and if I will take alpha common I will get 1 by 3 alpha 1 minus 2 beta by alpha. We know that beta by alpha is sigma, and if here I have taken alpha in denominator, I can take it to numerator and just simply say that this is equals to 1 by alpha by 3 into 1 minus 2 sigma. We know that alpha is strain per unit stress. Stress is stress per unit strain, and Young's modulus is change in stress per strain, and here the strain is alpha. We can say 1 by alpha as gamma. We can write is as gamma by 3 into 1 minus 2 sigma, because if we consider alpha to be strain per unit stress, and alpha is strain per unit stress, means the stress is unity, and here 1 unity by strain means stress by strain equals to Young's modulus. And now I have the relation K equals to gamma by 3 into 1 minus 2 sigma. This is the relationship, first relationship we have derived, where we have related Bulk's modulus with Young's modulus and Poisson's ratio. Now we are going to derive it for eta, shear modulus. So in this cube, a force is being applied along the surface ADEG, and we know that the tensile stress along BD will be equivalent to that of shearing stress along this surface. Let us suppose due to this shearing stress some deformation has taken place. Let this angle be theta. A shifted to A dash, D shifted to D dash, with making an angle theta with its initial position. Now we know that eta is equals to stress per strain. Here let us suppose this A dash and D dash be small l and length of the cube be L. Eta will be equals to T by small l by capital L equals to T by theta. Now we know that tensile stress along BD is equivalent to shearing stress along the upper surface. So a tensile stress will be there, and therefore a linear strain will be there, alpha will be there, and also a stress also being acted along the diagonal AC, which is contracting AC. Means here you can see that BD dash is longer than BD, but AC dash is smaller than AC. Means along AC the length is contracting, and as along AC the length is contracting, its lateral strain will increase BD's length. Means the increased length of BD will be equals to BD dash will be equals to its original length, that is L root 2 whole into the stress multiplied with linear strain and the lateral strain. Lateral strain is also making its length increase because the linear strain along AC is decreasing the length. It will means the lateral strain does the opposite work as that of linear strain. So now we have BD as L root 2 T alpha plus beta. We know that small l is here. Small l, here I have drawn the perpendicular, and as here theta is really very small, so we can see it as a right angle triangle, right angle isosceles triangle. So this BD, this increase, let it be point P. This PD dash will be equals to L cos theta. L cos theta and L cos alpha, let us suppose, and here the angle alpha will be equals to 45 degree, means L cos 45 degree, which will be equals to L by root 2. Cos 45 is 1 by root 2 root 2. Now the increase along BD will be equals to L root 2 T alpha plus beta, which is equals to L by root 2. So we can get the value of the strain, means small l by capital L, which will be equals to 2T alpha plus beta. So now gamma Young's modulus will be equals to the stress by strain T by 2T into alpha plus beta, which will be equals to 1 by 2 alpha plus beta, and taking alpha common I will get 1 by 2 alpha into 1 plus sigma, and if I take alpha to numerator I will get, here eta, because I have taken the small l by capital L is theta, tension stress by theta is shear modulus. So this will be equals to gamma by 2 into 1 plus sigma. So here we are present with this relation. So using this equation we are going to derive the relationship between sigma and k eta, sigma with k eta, and another relationship between k, sigma, gamma and eta. So let's start with the first one, sigma, eta and k. So I can cross multiply it. So it will be equal to 3k into 1 minus 2 sigma, and this will be equals to gamma, and this will be equals to 2 eta 1 plus sigma equals to gamma. Here RHS is same, so I can take LHS to be equal. 3k into 1 minus 2 sigma is equals to 2 eta into 1 plus sigma. So taking sigma to left hand side and taking it common, I will get sigma into 2 eta plus 6k equals to 3k minus 2 eta, and now sigma will be equals to 3k minus 2 eta by 2 eta plus 6k. So this is another relationship. So now we are going to find the final relationship, that is between k, eta and gamma. Gamma will be equal to 3k into 1 minus 2 sigma and 2 eta into 1 plus sigma. So I will have two equations containing these variables. So I can simply do this thing, gamma by k equals to 1 minus 2 sigma, and here gamma by eta equals to 2 into 1 plus sigma. Here I can also take 2 here. Now if I multiply this equation with 2 and add it with this equation, sigma term will cancel out, and I will get gamma by k plus gamma by eta with 3k equals to 3, because 1 into 2, 2, and 2 plus 1, 3. So now I can take the term gamma common and divide it on right hand side. I will get 1 by 3k plus 1 by eta equals to 3 by gamma. I will multiply the equation with 3. I will get 1 by k plus, here something is missing, let me check. Okay, yes, right, everything is correct. 3 by eta equals to 9 by gamma. This is the required equation. You can do it another way, where you have to take sigma as alpha by beta, means the equation where we put k equals to 1 by 3 into alpha minus 2 beta. You can use this equation, do the similar process, where you will get 1 by 3k equals to alpha minus 2 beta, and another equation will be 1 by eta 2 eta, yes, 1 by 2 eta equals to alpha plus beta. Multiply this alpha plus beta. Multiply this equation with 2, beta will cancel out. You will get 1 by 3k plus 1 by eta equals to 2 alpha. We know that 1 by alpha is gamma, unit stress per unit strain equals to gamma. So this will be equals to 1 by 3k plus 2 into alpha plus alpha will be equals to 3 alpha. 1 by eta plus 3 by gamma. Multiply this thing with 3, we will get 1 by k plus 3 by eta equals to 9 by gamma, the similar equation but in a different manner. Gamma will be equals to 2 eta 1 plus sigma. Gamma will be equals to 3k 1 minus 2 sigma. Taking the left hand side to be equal, we will get 3k 1 minus 2 sigma equals to 2 eta 1 plus sigma. Sigma the Poisson's ratio. So we are going to find limiting value of Poisson's ratio. So here if I take sigma to be positive, then this term will obviously be positive because eta is positive, 2 is positive, and obviously 1 plus something will also be positive. And here 3k is positive, but this thing needs to be positive. So for this thing to be positive, minus 2 sigma should be 2 sigma should be less than 1. So sigma should be less than 0.5. And if I take sigma to be negative, this term will be positive, but we have to consider this term because 1 plus sigma should be greater than 0 and sigma should be greater than minus 1. So we have the limiting value of sigma as sigma should be greater than minus 1, less than 0.5. And in actual cases, sigma of most of the materials lie between 0.2 to 0.4. And sigma is a number because stress by what is sigma? Strain by strain. As strain has no unit or dimension, and obviously strain by strain will also have 0 dimension and 0 unit. No dimension and no unit. So now I have to tell you about another case of that of wire. For wire actually things differ because wire has its outer layer stronger than its inner layer, so we can apply these equation on wire. This is for today. We will talk more about elasticity in upcoming lectures. Thanks for watching.